as an example for homework number 13. So in this particular problem, we've got two coupled nonlinear sets of ODEs. And so basically the first thing we want to do for this problem is we want to figure out how do we linearize these ODEs and then put them in a form similar to this, where we have, previously we had something like mx double dot plus bx dot plus kx equals some forcing function, but in this case, we're going to say m, instead of it being mass, is a matrix, k is a matrix, g is a matrix, and then x double dot is just simply denoting whatever variables we're dealing with of the second derivative form. And so given that in this set of equations that we're dealing with, we've got the variable that we're dealing with respect to is theta a and theta b, and so this x matrix is just comprised of theta a double dots and theta b double dots. And then using that same logic flowing forward, we see with x is theta a and theta b, so on. So how do we, first off, how are we going to linearize these, and then how we put it in something of this form? So basically, looking at this equation, there's not a whole lot to do to linearize this. As we saw before, using small angle approximation, wherever we see sine of theta a, that's approximately the same as theta a. And so that's really the only thing to linearize for this particular equation. There's no theta dot squares or anything else like that, and so it's pretty straightforward. So instead of just rewriting out the same equations with substituting this in, just leave it as it is. But in putting this in a matrix form, the way we want to do this is basically seeing in our first equation, where do we have any theta a double dots and theta b double dots, so on and so forth. So looking at these two equations, if we look at the first one, we see we've got a j in the theta a double dot direction, and so we're gonna, if we flip this, put our theta a double dots in the first column and theta b double dots in the second column, we would say that we have a j in the theta a and a 0 in the theta b double dot. And so for the second equation, we do the same logic. We see we've got nothing in theta a double dot, but we have an I in the b, or in the theta b double dot direction. And so using the same thought process all the way through, we're going to apply that to then theta a and theta b. Now it's seeing that sine of theta a is the same thing approximately as theta a. We're just going to say we have a negative mgd for our first equation, a 0 for theta b, and zeros across the board for our second equation. So yeah, that would be how we linearize it and then put it in this form, which is going to be useful to us in the nearby future. So the second part of this problem would be, after establishing this general structure and after doing a little bit of other algebra, we come to a point where we have this matrix A, which is affiliated with our system of equations, after finding the poles and stuff like that. So the question is, if we've got this matrix A, what are the eigenvalues for this particular matrix? And so the way that you want to find the eigenvalues of a system is knowing that generally you can think of it as just setting the determinant of a minus lambda I equal to 0. And so you're like, all right, well, what in the world is a minus lambda I to begin with before we even tackle the determinant? And so a minus lambda I, we've got our matrix A, and then lambda I is just simply lambda multiplied by our identity matrix, which should just be a 1 along the diagonal with zeros everywhere else. And so in this case, instead of being 1s, it's now lambdas. And so if we do a minus lambda I, this would just be our first term minus lambda, 0 minus 0, 0 minus 0, and 0 minus lambda. So taking those and putting them into a single matrix of a minus lambda I, as denoted here, then now the question becomes, how do I take the determinant of this? So I do this term multiplied by this term here, and then subtract this term by that term. And so when looking at this, knowing that we want this determinant equal to 0, when I look at this, we see 0 or minus 0 times 0 is useless. So we're like, all right, well, he's not going to affect the system at all. So how do these terms drive this to 0? And so we see when this lambda becomes a 0, obviously that's going to take this whole thing to 0. So we'd say that our first eigenvalue is at lambda equal to 0. And the other one, using the same exact thought, when is this term going to be 0? It's when this term cancels out. So we're going to be left with a lambda equal to a negative mdg over j. And so that's going to give us our second eigenvalue for the system. So typically, whenever you're dealing with eigenvalues, you're going to have either simply one eigenvector for this course primarily, but sometimes you might have multiple eigenvectors. It just depends on how your A minus lambda I matrix flows, like however things work out. So you just want to check. And so the question here is, all right, what in the world is the eigenvector of a system? And so how do we find it? And so basically, using our magic equation of a minus lambda I, we go back to it now knowing our eigenvalues, and we plug in wherever we see lambda, we plug in our first set. Let's say if lambda is equal to lambda 1, which is equal to 0, we're going to plug that in and find out what takes place. So if we plug in for lambda wherever we see it in this equation, so it'd be a minus a 0 here, a 0 minus a 0, a 0 minus a 0, and a 0 minus a 0 for that, and writing that in matrix form. So we now have, you could think of this as like a matrix of coefficients, which is multiplied by an effective matrix of U1 and U2, which is going to help us to find the eigenvectors for the system. And so as before, if we take these U1s and U2s and look at them as if they're rotating above here, our U1s are affiliated with the first column, our U2s are affiliated with the second column. So having these, looking at it now like that, we can rewrite out these two equations here as negative mdg over j in the U1 direction plus a 0 in the U2 direction equal to 0, because we want a minus lambda I, we want these two equations equal to 0. So instead of just saying this plus that is equal to 0, I'm just going to say one is equal to the negative of the other. So we've got a negative mdg over j in the U1 direction is equal to negative 0 U2, but negative 0 is just 0. So we got it equal to 0 U2. So in order to find out what is the eigenvector for the system, it's usually denoted by this big capital U, which is comprised of these little U1s and U2s. Usually what you want to do is find out these U1s and U2s, what is the ratio of these two things? And so the question is, how do I relate U1 to U2? How do I get one in terms of the other? And so basically looking at this equation, I'm not going to want to divide by 0 to find out how U2 relates to U1. Instead, I'm going to want to divide this negative mdg over j by, or divide it through on the other side so that I can get U1s instead in terms of U2s. So doing that, we see U1 is just going to be equal to 0 over negative mdg over j in the U2 direction. Hence, U1 is just 0 U2. And so if we were to rewrite this, column vector here in terms of just U2s, I would say it'd be pulling out a U2. What is U1 in terms of U2? It would be 0. So we saw before, U1 is equal to 0 U2, so I'd fill in a 0 here. And what is U2 in terms of itself? It's just 1. So that would be, this is our first eigenvector that's affiliated with our first eigenvalue. And so if we use that same logic again for the second eigenvalue and doing the same thought process, where instead of plugging in a 0 to these, we're going to plug in a negative mdg over j, negative mdg over j, fill out the matrix, and then once again we get these two equations. I didn't mention this before, but when looking at these equations, we see in the first one, when I say this term plus that term is equal to 0, all I'm saying is that 0 plus 0 is equal to 0, or 0 is equal to 0, which pretty much tells me nothing. This is just a trivial solution which we're not interested in. So in the previous one, I just kind of flew by this, but we only used the first equation. We didn't even look at the second one. But as you see, it's the same concept where 0 is equal to 0, so we're not even interested in that one. In some cases in linear algebra, you can run into scenarios where that's not the case, and you can get two eigenvectors for the same eigenvalue. But in this case, conveniently, both of these result in only one eigenvector per eigenvalue. So in this one, 0 is equal to 0, don't care about it. But in this other case, we have 0 is going to be equal to a positive, when we put them on the other side, a positive mgd over j. So we have a 0 in the U1 direction is equal to a positive mgd over j in the U2. Therefore, not wanting to divide by 0, do the same thing as before. And now, instead of having U1s in terms of U2s, I now have U2s in terms of U1s, where it's just U2 is equal to 0, U1. So writing out the second eigenvector, it's going to be U2, which is comprised of U1s and U2s, these little guys, is going to be equal to U1. And how does U1 relate to itself? Just 1. And then what is U2 in terms of U1? It's just 0. So we now have our eigenvectors for U1 and U2, which is affiliated with our first eigenvalue and our second eigenvalue. And then after obtaining these, generally you want to put, like, usually we call it x. Here we've got them in terms of theta a's and theta b's. We want to write out this expression in a more specific form. So it's like, what is theta a and theta b? It's going to be comprised of, it's generally written as something that's like C1, I think in the book it's just like U1, can't remember the exact form, but generally it's like C1 V1 e to the lambda t. And so here we see it's comprised, or this giant equation here is just comprised of a bunch of c's. Our V1 here, which is affiliated with our first eigenvector, this would be C1 V1, C2 V2, C3 V3, C4 V4, where V1 and V2 are our first eigenvector, and V3 and V4 are our second eigenvector. And we notice that these p's here, those poles of the system, are affiliated, they're directly correlated to our eigenvalues. So we see P1 and P2 here, C to the PT. The P1 and P2 are affiliated with our first eigenvalue because they're both 0, and our P3 and P4 are both affiliated with our second eigenvalue, where one is the positive square root and one is the negative square root, hence 2 poles. So we've got this expression, but it's still not fully solved. We still don't know what C1, C2, C3, and C4 are. So in order to solve for these things, we would recognize, well, we need some initial conditions to solve for these 4 constants. So basically you got 4 equations, 4 unknowns we could solve. So using basic linear algebra, we know that we could say this thing is just equal to, or when we're taking, let's say, the initial condition of theta A and theta B of 0, we know what this does to these p terms, or these t's. If you're filling in a t equal to 0 for all of them, then all these e to the t's are going to go to 1. And so if that's the case, then we could just say this is just now, instead of any e terms, it's just a C1v1, a C2v2, and so on. And so we could just make that a set of 2 different matrices where we've got this row vector, which is just u1, u2, u3, v4, or as I described them here, v1, v2, v3, v4, like that. And then we've got these coefficients c here in this column vector. And so if you just simply thought of it as taking this vector and rotating over here, you would see there'd be C1 times U1, C2 times U2, and then so on. And so, as we know in basic linear algebra, we know that if we had A is equal to, the matrix A is equal to B times C, we could say, all right, well, if I'm trying to solve for one of these, let's say this is the matrix, we should rewrite this out as thetas, U's, and C's. I could say if I want to know C, I would say it's equal to U inverse times theta. And so, see here, that is exactly true. So our matrix of unknowns constants is equal to our inverse of U matrix multiplied by our theta matrix. And so yeah, that's how you solve for eigenvalues, eigenvectors, and express theta in terms of its form that you wanted in. Hope that's helpful.